I'm going to improvise a bit because we wanted to start already in the computer room. So, but let's try to do something like that. Just in case if I will finish earlier, you are free today. So I think it's not that bad idea. So this is the workshop I'm going to perform together with Misha. How do you know Misha? He's here. So he's my PhD student and he knows everything about CIGALE. So we are going to do it together. The main problem here is that we are mostly cosmologists and we are going to completely different scales. Yes, now we are going to the galaxies. And something that you have as a given, like for example, stellar mass, star formation rate, etc., it's not really given by that, but we have to calculate it. And I wanted to tell you how we are doing it, and we also want to show you how you can do it by yourself. If you are interested in galaxy evolution, or if you want to know galaxy properties in a different survey, for example, you can do it by yourself. I will show you how to do it in theory. Then I will show you the different, like one tool which I'm using, which I like the best, but of course you have many different tools to calculate those base properties of the galaxies. And then tomorrow we are going to have a hands-on workshop, so I will give you some galaxies, we will explain you how to use CIGALE, and then we are going to play a bit how to fit the spectral energy distribution of galaxies. And if you are completely not interested, I'm not going to, to force you to come, but I hope that at least some of you would like to know something better and we can discuss those things. Okay, so as I said, first, I'm going to tell you what the SED is, like spectral energy distribution of galaxies. Yes. So it's not just a point, but it's something else. I will give a short introduction to CIGALE, but tomorrow I think Misha will give you even more detailed introduction to different tools we can use, and then we are going to play on together and maybe we can also do some competition, who knows. Okay, so let's start with SEDs. So you know that galaxy emits energy in a different wavelengths. All wavelengths, electromagnetic wavelengths, you know. And so we can see the radiation in different instruments, in different wavelength range, and the same galaxy can look completely different using different instruments. As you can see here, this is the same galaxy as it's seen by Chandra, by galaxies in the ultraviolet, with optical data, with near infrared, and with radio. And you can even think now about the galaxy as the human body. Yes. So if you are, for example, sick, you have to check different things in your body. You have to check the blood pressure, etc. So we can do it the same in the galaxy. You have to know, if you want to know what is going on in the galaxy, you have to go into a very holistic way to understand what is going on. Yes. And the distribution, like the whole energy emitted in different wavelengths, we call the spectral energy distribution of the galaxy. And this is something we are going to talk about. But of course, we don't really use those beautiful images. Of course, you can do it, but like for the huge survey, if you want to calculate, for example, the stellar masses of hundreds of galaxies, we are not doing one by one using those beautiful images. But you are using something which we call the broadband photometry. So each point from different wavelengths, we are converting to one point on this spectral energy distribution, and we have the wavelength and the flux density. Yes? And given we have different observations in different wavelengths from different instruments, at the end we can construct the spectral energy distribution, and we can try to fit and model different physical properties in that galaxy. Just to let you know what the broadband photometry is. So it's something not maybe very cool, so it's just the average flux in a specific wavelength range. So if you have the spectra of the galaxy, it looks very nice. You have all the information about different lines, absorption, emission, but in broadband filters you have just the one flux from the whole redshift, from the whole wavelength range. And for example, from the beautiful spectra, we can have 4 different points we are putting on our SED. So I think this is so you see that in that case, using broadband photometry, we are using some information about the very specific information about the, for example, lights. Yes, so this is something we are not using in the broadband SED fitting, but of course we can do it in a different way. And you see here, it's an example I really like. You have a different spectra for different galaxies. Of course, they are somehow average to show you. And you see that it's very important to have knowledge about the whole SED, because for example here, in the optical range, which is comes up to around 8 micrometers, galaxy, the shape of the optical broadband SED looks very similar. Yes, of course, not for all the galaxies, yes, but it's very similar, and can say that you cannot really decide which galaxy is which, like which one is elliptical and which do not really produce the stars, and which one is really starbursting and has a lot of production of new stars, a lot of dust, etc. So it's very important to know what is on both sides of the star part of the SED, but also the dusty part, which I like the most. Yeah? So it's important to calculate the final properties of the galaxy. It's very important to know all of it about the galaxy. And of course, to make the final shape of the spectral energy distribution, you have to know something, and you have to assume something, you have to use different models, which are not really just the function we are going to fit, which is the nicest one, but it really has a physical meaning, yes? So you have to have some assumption about the initial mass function, yes? So we have to give something to the program, yes? Also about the transformation history, you have different scenarios. For example, you have one burst and then nothing really happened in the galaxy, the new stars dying very, very slowly. Or you have different bursts during the life of the galaxy. You also have to have some assumption about the stellar population which you have inside, about the metal content. You see that those are very, very detailed information we are going to assume. And of course, the dust characteristic, what is the amount, and what I really the most, so the dust attenuation, so the amount of energy emitted in the UV and then re-emitted in the infrared, and other things. Yeah, so it's not the full list, of course we have more, but those are the most basic ones we have to assume in our book. And you see that from those points, which we don't have many, usually you have just a few points on the galaxy, you can try to estimate different information about how does it work, how it shaped the old stellar population, the young stellar population, which you have here in the UV part, and then the whole dust emission and attenuation. So you can obtain a lot of very important information just from your few points, but remember that you have some assumption behind. And if you have one galaxy and 3 different people trying to fit the SED, you will obtain at the end 3 different information, because they can use a different, for example, initial mass function or different attenuation. So you have to be very careful. And usually when you have a galaxy with stellar mass, it's not the end, because it has some errors. And if you use different tool, you will get a different stellar mass, just a bit, but different. So be careful if you compare different galaxies for different SED fitting. Remember that in the background you have some assumptions you have to use to calculate those properties. And this is a very nice plot prepared by Misha. So you can see that on the SED of the galaxy, you have those different ranges of wavelengths when you have the most important information. It's not that only in that part you have information about the star formation rate, yes, but this is those are the main parts. So in the UV part you have information about stellar population and the number of new stars, because new stars produce new very massive and blue stars. They are emitting a lot of ultraviolet. Yes, so usually here, if you have a data from ultraviolet, you can somehow direct calculate the star formation rate and the amount of the new stars in the galaxy. Then we have some information about the dust, about the different dust grains, about different distribution of the dust in the galaxy. And then we have the whole range, like from the near infrared, even almost radio. you have information about the dust. So the dust, which re-emits the energy from the young stars. So as you can see, having just the part of the information about the galaxy, it's not enough to calculate the proper final information about the galaxy and the main properties. But of course, it's very difficult because some of the parts of the galaxy, like some emission, is not visible from Earth. From Earth, you can do some measurements of the optical data. But if we are discussing the ultraviolet, we need some satellites. The same from infrared. We have very narrow windows for the infrared to observe from the sky, from the Earth. So it means that we have different instruments with different resolutions, and we have to match somehow data from different instruments together. So of course we have some uncertainties as well. Yes. So even in the small scale, we have a lot of uncertainties, and we have to somehow deal with it. But as I said, from the electromagnetic wavelengths, from the electromagnetic spectra, we can have some information. So if you have a measurement about, for example, from X-ray, you can say something about, for example, the hotness, dust, yes. Then, as I said in the optical, so this is something that we have the number of galaxies with optical detection is the largest, yes, because it's the easiest from our point of view. Then you can say something about the all-star population. But if you want to calculate the saturation rate, you need some information also from the ultraviolet and the infrared, and etc. So you see, we have to deal with different things. And of course, we also have the AGS in the galaxy, so you have to somehow include in your SED fitting, and this information you have, for example, in the radio data. So we have to somehow use it, and that's why I said that the astrophysics is full of colors, different instruments, different resolutions, and I think a lot of fun, and you will see it tomorrow, and you will enjoy it. Yeah, I think that is going to stop soon. So, for example, here, how you want to fit SED? Yeah. So, as I said at the beginning, we have those broadband measurements. We are putting somehow on our wavelength flux density distribution, and we want to obtain this line, the black line, like in the physical sense. Yes. So we want to obtain some physical models from that. And then you have two different schools. First one is that you are treating in a different way the stellar part. So we are calculating all the stellar properties using one tool, and then you have the second tool and the different approach for the dust part. And it was done in many papers that you can have this division, yes. But then both the stellar and the dust emission is separately, and then we have a problem with the dust attenuation because we don't really know how to fit that attenuation, the amount of energy which is re-emitted in the dust from the star-forming regions. Or we can fit everything together and to use the data in a consistent way. So to trying to find the best models, which are, for example, you can see here, the dust emission starts with the dust part. But also you have some of the tail of this emission also visible in the optical. Yes? So that's why I think that, in my opinion, we should fit the spectral energy distribution of galaxies using like the whole spectra and all possible information we have to obtain at the end the best physical properties used also later on for small. Yeah. So what we can model. The basic thing. So we can model the stellar population and the amount of stars, the stellar mass, combine the old stellar population and the young one. We can also model the dust emission, gas content, and etc. And in the tool I'm going to show you in CIGALE, we are using the energy balance. So we are really taking care of the energy emitted from the young stars and re-emitted in the dust. This is the energy balance assumption. which I think it works very well, but of course I'm not saying that CIGALE is the best tool. Of course you can use it in something else. And this is a very nice example I like to show from the Spectral tool. Different tool, you see, I'm not saying that the CIGALE is the ultimate. So here, for example, you have a real galaxy spectra, real simulated galaxy spectra, and we want to obtain the main properties of the galaxy, so the stellar parameters, dust parameters, and the AGS. And at the beginning, we have just one photometric data from the R filter from SDSS. And you can see that and here on those blue lines, they are the real values. Yes. So you can see that even with one parameter in optical data in the optical part, you can somehow guess, for example, the stellar mass. Of course, it's not perfect, but you can guess somehow where it is. Yes. So of course the error is huge, but you can do something with two. The stellar part, the old stellar population can be fitted much better. So you can see that with two, you can really shape this part. Then we have the full SDSS UGRIC photometric band, and you can see that now we are almost done with stellar mass. But here with the dust, not really. You can see that we have the whole range of different models which really fit the data. They are the same, like the upper one and the lower one fit the same, and they look that they are good. Yes. So, but we have to somehow choose the best one. Now we are adding some near-infrared data, so we can see that we can shape much better, for example, the specific star formation rate, which is the star formation rate over the stellar mass, and etc. So you can see that it's better and better with ultraviolet data. So we have now also the information about the young stellar population. The stellar mass is perfect. It's exactly what we wanted to obtain in the beginning. Also the dust attenuation, because we use both UV and infrared part. You have a very nice peak, very close to the true one. But we can also add far-infrared data, and you can see that even the parameters which are saying about the properties and the amount of the AGN influencing our SED is much better. So you see that it's very important to have the full information about the broadband photometry, because using all of those information at the same time, we can really shape all the main basic parameters which then are using, for example, in the cosmology. Okay. And then we have, of course, it's more complicated. It's not that we just pushing enter and then that's it. As I said, we have to choose different things. Like for example, we have to choose the stellar population models. Yes, so we have the whole range, and you have to you have the power. Yes, because you can use different parameters, and of course you can fit something which is not physical. So we have to be careful about that. But you have the whole range of different possibilities you can use. As I said, also the initial mass function, the star formation history is all here. Yes. And as I said, the star formation history, you can have different things. You can have a constant one. You can say no, it's declining after some time, and you have to say when exactly. Or you have just delayed one and rising. So it's also under it's up to you which one you are choosing at the end. But you have to remember that you have some help from the information about the survey itself. Yes. So somehow the selection function of the survey. So you know that, for example, you have more and more galaxies like the star forming one. So you know that you should have some young stellar population at the end. So something should be here, yes, not the declining one, but so those kind of information you have to use. Then the dust emissions, so using different instruments, which we don't have many, but thank God we have JWST. So we can also somehow decide what we have in the dust part. Which kind of models we have, because you see that even here on this very simple one, you have different shapes, and as you can see on the optical part, they look exactly the same. For dust attenuation and the dust emission, as I said, you can play with different parameters. You can decide which shape you want to have. And there are thousands of parameters which you can use, and you can decide. And remember that the final results you have, they are somehow weighted on the first choice you did on the very beginning. And that's attenuation, the one I love the most, which says how the energy emitted in the ultraviolet from the young stars is re-emitted in the near-infrared. So you can see that the difference here is huge. And I will tell you probably more tomorrow, or Misha will tell you more tomorrow about that. And this is also something probably Misha is going to discuss, that the dust is really a key to find the best properties of the galaxy, because it can hidden some very important properties of the galaxy, and so you have to treat it very carefully, and you have to really try to find different observations which you can use to somehow shape it better. Yes, so it's, because the dust is involved in many different things. Yes, the interstellar medium, in the star formation, and you have, of course, you have dust close to the newborn stars. So it's very complicated thing. As you can see here, I'm not going to describe everything what is here, but it's really difficult to treat it in a very good way. Yes. And especially that we don't have a lot of information about that. We don't have a very good measurements. And again, one more very similar drawing from Darko-Doniecki, and you can see the whole cycle when you have the dust and the byronic matter, and how much it plays together in the galaxy, and how much it is mixed together. So this dust attenuation, as I told you, maybe you don't think about it as it's super important, but you can see here, this is the real galaxy we're fitted with Veronique Buat. And you can see that the galaxy and the observation, you have a very good observation of those galaxies. You can see all those blue points there from observations. But what we should see, like without the dust, is that line. So you can see the amount of dust, which is the amount of ultraviolet light, which is hidden by dust and re-emitted in the infrared. So you see that it's a really, like, in my opinion, is a main player in the SED fitting. AGN emission addition, so you can use it if you know that you have the data to do that. Okay, so if you don't have mid-infrared data, you can see the difference between different AGNs like type 1 and type 2, or you don't have any information from the far infrared and radio, don't use it. Okay, so it's important because it's also very complicated. And so from all those information about the galaxy from different wavelengths, you can also see, for example, that the observation in the infrared are completely different. They have completely different resolution than those for example, in the optical. And it's very difficult to match and to decide if the whole flux you can see, for example, in 500 millimeters, becomes from they are just the counterparts of the same galaxy, because you can have you can also think about the blending. Yes, so it's very difficult. But now we have more and more information, for example, from X-rays, and for example in CIGALE we can use the X-ray information. We can shape a bit our knowledge about galaxies. So more and more information comes also from the LOFAR data. Using LOFAR, we can also shape a bit the information about the AGN component and the AGN contribution to our galaxy. As you can see here, for example, this yellow line is the contribution, the blue line is the contribution for the AGN. So you can see that it changed completely our view of the galaxy in the mid-infrared part of the galaxy. So we can use also both, and then it's perfect, but we don't have a lot of galaxies with both. So part 2, CIGALE. So in my work, I'm using CIGALE. This is the program I like the most, which I think is also very easy to use, at least now. So in this program, we are using this energy balance, so the relation between UV and infrared and other stuff. And I think it's I think it's very fast if you already installed CIGALE. It's a problem today. But you can obtain all the main physical properties, and the whole team of CIGALE is very, very nice. You can always ask people which wrote the program, that you can ask them some problems, or you can ask for advice. And I think that it's also very important to have this very friendly atmosphere and to discuss with them. In CIGALE, we are also creating using different models and different parameters. We are creating hundreds, thousands of different models, and then we are using the Bayesian like statistical analysis. So what is really important at the end, if you want to, for example, calculate the stellar mass, you have really uncertainty at the end. So it's like it's not just a one value, because I know programs which can do that, but I will not name them now. But yes, I think that it's very important, and I hope that tomorrow we can also show you the PDF analysis and how the errors are calculated. We are going to use tomorrow different models. So we are going to use different population history, single star population, nebular emission, data attenuation, data emission, AGS, and etc. We are not going to use X-ray and radio because we don't have those examples for you prepared. But we are going to use all those models, and we are going to pick different galaxies we prepared for you. One very nearby galaxy, and four, I think, like 0.3, something like that, redshift, and the rest we also prepared like 100 galaxies, which we can use in the very statistical way, so we can fit them all together to check the properties of the field and of those objects in a more global way. So we can also try to fit, for example, the main sequence. Yes, so this is also something nice to know. And yes, the part 3, I think we'll start tomorrow, because what we want to do, we want to install the CIGALE program in the computer room, and I think that we will have a lot of fun doing that. Do you want to add something?
I think that's all. I mean, tomorrow we will play. So tomorrow we can play with different attenuation modes and different attenuation history and see how they affect the. Tomorrow we can check the different transformation histories, different attenuation laws, maybe different infrared emissions.
Oh yes.
And see how they affect the physical properties of the galaxies, such as the star formation rate, the stellar masses. You can play with yourself with the modules and test the data.
Yeah, and don't be scared. I told you that we have all those assumptions we have to do, and all the different parameters. But don't be scared, it's not that bad, yes. And I think it's funny also to find the best parameters, and at the end, from those points, as I showed you somewhere here, you will have some points, and then at the end you can say what is the stellar mass or what is the transformation rate, if we have AGN inside or not. I think it's nice, and it gives you the happiness very quickly. You don't have to wait many hours for the simulation, for example, and those are real data. Yes. Do you have any questions today? Okay.
Yeah, so for set analysis, we must find observable flux, yes, or we must use the spectrum.
No. We are going to play only with flux.
Only with flux.
Yes. And I forgot to tell you that it is also very important is to know the redshift of the galaxy, because of course all the properties change to redshift, and of course you can use even CIGALE to calculate the photometric redshift, yes, but this is the main ingredient. You have to have a redshift and flux. And of course you can use, for example, like some open source, like open database, like SED or whatever.
We can find the flux in different For example, from Hubble Space Telescope, I can open the archive and find some observation clocks. Yes, and I do it for each energy band. Yeah, sorry, this is wavelength. Okay.
Yeah.
Okay.
Yeah, so and then it's, you don't need anything, like, to be honest, you have to know how the tool works. You can download whatever it is from the iCard, and you can play it, you can know exactly. Because you have to also remember that if you are searching for a specific galaxy in a huge surveys, they are all doing it in the automatic way. So we are doing it that we have some parameters, and we are using the same parameters for the whole range, but for the whole galaxies. So of course, not all of them are treated in such a good way. Yes.
Yeah.
So then you can check it by yourself. And
And also, I saw on the slides year zeta. So now data from year zeta are presented in open.
this one I used, I cannot find it now. I don't remember what was it. But from Erosita, yes.
Yeah.
The Erosita is one of the second PhD student of mine. He's working on the Erosita data, and some of them they are published. And he already did the exam for some of them. So you can also use it. You have to, and I think that on the Erosita website you have already the cross-match catalog. So you have the X-rays and the optical data. So then what you have to do, you can also try to check something in the infrared or whatever. But it's ready, and then you are ready to go and done.
Okay, thank you.
So you talked about redshift. So this can be the redshift, I guess, yes. And if it is, can you fit both redshift and yes?
Yes, you can do it in the
At the same time?
Yeah, but I don't think that it's the best approach, because then you have to use different parameters, because you have to also use different, because CIGALE in general was not created as the photometric redshift tool. So you have to use a lot of parameters, and at the end you can overfit everything. So what I'm doing, if I want to use CIGALE for the photometric redshift, I'm using very simple models and very just a few parameters to find the possible redshift, and then think again. So that's why I think that it's better to, for example, to use LOFAR for the photometric redshift, and then CIGALE to obtain the physical properties.
Okay. And then here you have prospector. So what's the main difference between prospector and CIGALE?
I don't remember now. Yes, I think that it was something with different modules, so you couldn't use your own modules. Because in CIGALE, it's very easy to change modules, or you have to write your own function, like to calculate something. And I think in Prospector it was not that easy.
So for example, if I have some star formations with templates or on my own, I can put them in input of CIGALE.
Yes, yes. And you can also use a prior. So for example, if for example, Francesco will calculate the metallicity of the galaxy, we can use it as a prior.
Okay, that's good.
Any other questions?
Yes, thank you for the talk. I want to ask, compared to the spectral energy analysis of just a star, what are very distinct features exclusive to a galaxy when you do the analysis of the galaxy, which are not taken into consideration in stars, but are very important for the galaxy?
Very important for galaxy. Okay, so for me, the redshift, of course, the stellar population, and which is very easy. If I understand correctly your question, so I think that both the redshift and the stellar population, the stellar mass is very easy to calculate, and you can use it immediately for any other analysis. Yes. But for me, the most important is if you have the stellar mass, the star formation rate, so then I can calculate the specific star formation rate, which is for me, it's better to use because then I'm not biased yet. And for me, of course, the data. and the dust emission, yes. So that, I think that it's also important to know something about AGN, but as I said, it's difficult if you don't have enough data. So I'm going on if I don't.
So I'm working with AGN in nuclei.
Mm-hmm.
So in nuclei we have many different physical models, and we must so we must choose physical motivated model for describe the emission of active galactic.
Yes.
Here we have multi-wavelength analysis, and here also I will have many different models.
Mm-hmm. Yes, here, I don't know, here. So in CIGALE, like by default, for AGS, you have two models. One is the old models of Fritz 2006, which is just here. So you have galaxies which are type 1 and type 2. You can also play a bit with the different optical depth, etc. But this model is very simple. So what you assume here is just that the torus is homogeneous, and you have no additional, for example, dust attenuation. Yeah, dust attenuation for the torus. But now, since 2000, I think, we also included the SCIRPA. It's the Asian model prepared by I think it's 2016, and in that it's more complicated, so you have more data. So then you can also, you don't assume that the very homogeneous torus, but it's clumpy torus, and moreover you also can add the attenuation of the dust along the torus. Yes. So I think it's more complicated, but it's more physical. Yes. So you can choose between those two. But as I said, if you know the formula, if you know if you already have some recipe to calculate, it's very easy to add to the CIGALE. It's the Python script. You just have to write one module and add it inside.
Yeah, but another part of spectrum, I mean, if we want to make stellar mass or star formation rate, it's also a few models or many different models, and we must choose physically motivated.
Oh yeah, yeah. So for example, what I said about the physical motivated. So of course you can fit a galaxy. We did it by mistake once with 100% of AGN contribution. You can fit, and at the end you will have all the properties with nice error bars and etc. But you know that it's impossible. You know that the galaxy is a normal galaxy, so you have to think about those kind of things. But it's for tomorrow. But for other, you have here they are the basic one. You can use, so for example, for the star formation history, you have different models with a burst, with a quenching, but you can also put your own star formation history. For stellar, it's much easier because I think that 90% of people are using Bruce-Wire Shadow model. So it means that it's easier to compare with the literature. Yes? So using one. With the initial mass function, we have 2 or 3, 2. Then we have different infrared models and those 2 AGNs. And it also depends what you want to do with the data. Because if you want to compare with other results, it's better to use similar models. Yes, because we cannot really compare I don't know, like the AGN from like the galaxy without AGN with those with IGN. Yes? So it's better, what I really prefer, to check first with whom I want to compare, and then to choose accordingly all the models. Yes? But it's not that bad, really. If you do it once or twice, you know exactly what to choose. So I think that is the best idea is to practice. That's why I really hope that tomorrow we will have a lot of fun with practicing on those guys.
Thank you so much.
Welcome.
I had a question what kind of different dusts are there, and is some dust like more useful, or is some dust like more, it's giving me more information?
All the dust is very important. No, the dust in general is very important. But if you are thinking about different modules, It's just saying like different models can tell you about, for example, about the concentration, about the size of rings, and etc. Something you really is difficult to find. Yes, like in your broadband SED. But wait, I will show you something like here. I have the dust emission. Also, you see that for me, from my point of view, if I want to play more with star formation history and the star formation rate of the galaxy, I'm more, for me the most important is this part of the spectra of the dust. Yes, because I can see here the far infrared. Okay, maybe maybe you can do it a different way, but I remember I have this very nice plot somewhere. It's up here. So if I want to play with the star formation history and the star formation rate, for me more important is this cold dust. Yes, so the measurement of the cold dust. If I think that I have the AGN, which can have a very large influence on on my galaxy, I want to see the hot dust, which is here, because I can see the different peaks given by the dust itself. So it depends. What do you really want to do? If you really want to study the dust properties, then the most important is that part of the spectrum. Or if you want to study the whole properties of the galaxy. It's difficult to say, Misha, maybe you have a better answer than I have.
Maybe you can put maybe the plot right?
The nice one? But which one?
The one before, yes.
Yeah.
Yes, so here we can see, for instance, like, so the direct star formation rate, tomorrow you'll see all of this more details, but so the direct star formation rate comes from the UV and short wavelength usually, but the majority of these photons are absorbed by dust, and they are emitted in the infrared. So this is why the infrared emission is the hidden star formation rate estimation. And different dust modules give different information about dust. So some modules give you better estimation about temperature, or some modules you can play with different grain sizes. As you can see, you will see tomorrow with the grain and beam model, right,
Yeah.
Kasia? So yeah.
But it's really based with the data you have. Yes, sometimes you can use a model which at the end will overfit your data.
Any other question?
I have one comment. No, because we prepare the computers for you with the computer room. But if you have a laptop, but preferably with Linux, because we don't know how to install on the Windows.
Is it possible to install it in Mac too?
Oh yes, it's also just the Windows. I have no idea how to work with Windows. You shouldn't work with Windows. And so you can also bring your own computer, and we can do the installation. So then after the workshop, you can still use it, and you can play by yourself. Yeah.
General information. So everybody, if you want to do cosmology, get rid of your Windows.
If there are no more question, I have a question. This initial mass function, that is also one model that goes into the code, right?
Yeah.
So what about CIGALE? Like, because in CIGALE also you didn't mention about initial mass function.
You have different initial mass functions. For example, you have a group and subfitter, and yes. And they can really change at the end your results. So they can say they can just change one thing, which is the stellar mass. But you have it's just a shift between a stellar masses. But if you use this, for example, to calculate the star formation, the specific star formation or whatever, then it really changes the results. So you can do. I have somewhere. It's very nice, but. Or you have just here, you have two different group and saltpeter. So you see that it's not exactly the same. You have some changes, yes, in the models, which you can really see in the stellar mass here.
Okay, and also like when we fit the SED, like we fit using chi-square.
Yeah, chi-square very good.
Okay, so how about this degeneracy that can cause between parameters while fitting? How does CIGALE take that to work? Or any other course?
Yeah. So in that case, I think I really need some cloth somewhere. Like, okay. Yes, so with different modules we are choosing, with different parameters, we are creating just like a number of different templates, yes? And of course, your final result depends on the templates you create, yes? And the best one is by CIGALE, the chi-square analysis, will be that one which can fit the most, which can, we can cross as many possible observations that we have. But remember, it's just a code, yes? So for example, if you are going to have, because what we try to do, for example, we try to use like a normal spectra, like a high resolution spectra together with photometry. And if you have like, for example, hundreds points here, and just a few here and here, you will not fit it. So of course you will fit it, you will get the answer at the end, but the whole way it's going to be put just here. Yeah. This is the problem with all those. That's why I think that, but we can also learn tomorrow that we are going to, which CIGALE is doing automatically, we can do the mock analysis. So based on your data, you are creating like artificial catalog, but it's done by CIGALE itself. And then you can check if the results from mock analysis are similar to those which you can obtain from the real data. If they are completely out, it means that something went wrong and your models are not good. Those kind of things.
Or even check the PDFs of when we have less galaxies.
I will show you, but now it's on the computer, which I left somewhere else. Yes, so yes, that's true. If you have, because you can do the mock analysis if you have some of galaxies, I don't know, 20, 1,000 or 300, whatever it is. But if you have one galaxy or two galaxies, you don't really do the mock analysis because it's kind of pointless. We can also show you tomorrow. But you can check the PDFs if the different models are really peaking in one place, etc. I will show you tomorrow.